What if our universe is only a portion of a much larger cosmic world rather than the entire cosmos? In fact, the perplexing discoveries made by the James Webb Telescope have been raising questions about whether the universe's development could have actually occurred as widely believed for some time now. This is because the Webb keeps finding equally early and mysterious objects that, in our opinion, shouldn't actually exist. However, if other universes do exist alongside our own, how could we possibly find these hidden parallel worlds? The intriguing response is that we might have already done so, and that there are direct remnants of a previous cosmos out there. The 6 unexplainable early galaxies, for instance, were as massive as the Milky Way is today some 13 billion years ago, and thus stand in stark contradiction to current cosmology. The situation is similar in the case of the galaxy Jade's GSZ 140, which existed as early as 290 million years after the Big Bang, and is also surprisingly large and starry. But how is this even possible? The James Webb Telescope is keeping the astronomical world on tenthooks and is now regularly reminding us that we are still a long way from having solved all the mysteries of the cosmos. If our standard model states that the normal matter needed for this simply did not yet exist, then how could there have been such massive star clusters at that time? Confused astronomers note that the matter density in the young universe was either 2 to 5 times greater than generally assumed, or that the galactic early birds grew in a completely different way than previously suspected. Either way, the so-called universe breakers are putting the experts in a difficult position, but the same also applies to completely different objects. In fact, the James Webb Telescope has identified a black hole elsewhere that existed just 770 million years after the birth of the cosmos. And despite everything, it already weighed over 1 billion solar masses. The researchers then analyzed the feeding mechanism of the gravity monster, but to their own amazement, they found nothing unusual. Apparently, the black holes of the early universe grew in a similar way to their later counterparts, which, to put it another way, means that we apparently know significantly less about the development of galaxies than we thought. What we do know, however, is that the universe also behaves idiosyncratically when it comes to speed. More precisely, this refers to the value of the so-called Hubble constant, which indicates the speed at which the universe is currently expanding, and on paper the expansion rate is around 67 kilometers a second per megaparsec. A quick explanation. 1 megaparsec is about 26 million light-year, while 1 light-year is 9.46 trillion kilometers. In other words, this means that the speed at which the galaxies in space move away from each other increases by 67 kilometers per second every 26 million light-year. That's an impressive 244,000 km per hour per megaparc, but it can be significantly faster than that in practice, and this is the crucial point. Our theoretical predictions simply do not match the real observations in space in detail. Direct measurements based on supernovae gravitational lenses, variable stars, and red giants have shown that the value of the Hubble constant is actually 73 kilometers per megaparc. This in turn corresponds to 264,000 km/h per megaparsec, and thus a deviation of 20,000 km/h per megaparsec from the theoretically predicted value, and indeed this expansion puzzle, which experts collectively refer to as the Hubble tension, was recently confirmed once again by the James Webb Telescope after James Webb re-examined the data previously collected. By the Hubble telescope, it was once again established that the universe is simply not doing what our understanding says it should. The overall result this time was also a Hubble constant of 72. 6 kilometers per megaparc. But what do all these confusing findings actually mean for the big picture? Could it be that we are likewise headed in the wrong direction with regard to much more fundamental issues if we have been so wildly wrong about the rate of the universe's development and expansion? What if our universe is ultimately simply a piece of a much more intricate cosmic puzzle? A cycle, a multiverse, or something entirely different? What if the much-anticipated Big Bang also occurred somewhat differently than usually assumed? Well, the perhaps somewhat surprising news is that such theories are anything but new, and that they have been the subject of serious discussion among experts for quite some time. And although the idea that our cosmos is not unique at the end of the day may sound rather like science fiction, at first parallel universes are by no means inconceivable. From a purely physical point of view, in fact, they may even be probable. And yet the theories as to how the many worlds can be explained in detail sometimes differ widely. One approach is based on the assumption that our universe is subject to an eternal cycle of destruction and resurrection, and it has its most famous advocate in the person of the British Nobel Prize winner in physics, Roger Penrose. In principle, Penrose is convinced that the universe will eventually return to an extreme state from which it can explode into its new existence in the best Big Bang manner, and not just once but over and over again. The cosmos would continue to expand until all matter has disintegrated and become light, and in doing so, it maneuvers itself into a state in which nothing has a time or space reference to each other anymore, and which, according to Penrose, inevitably leads to a new Big Bang. But assuming that this cosmic interplay really corresponds to reality, wouldn't there have to be some tangible evidence for it? Well, actually, yes. And according to Penrose, we have already found it more specifically. These are the so-called Hawking points, which could be nothing more than the direct relics of a precursor universe. As soon as black holes evaporate completely into Hawking radiation at the end of a cosmic era, they would take all of the radiated energy with them into the subsequent universe in the form of such a Hawking point. In theory, these telltale remnants of the microwave background radiation of the new cosmos then look like disks about the diameter of the full moon, and in practice Penrose's team has detected exactly that in the data from the Planck and WMAP satellites. No less exciting in turn is the theory of the mirror universe, which states that our universe has an inverted twin. In simple terms, this hypothesis is based on the fact that the Big Bang not only marked the beginning of our cosmos, but also that of a second one with exactly the opposite properties. This means, on the one hand, that in our twin world there is more antimatter and mirrored spatial conditions, and on the other hand, that time also runs in the opposite direction there. And indeed, the idea of a mirror universe is even capable of providing answers to some profound questions, such as why there is more matter than antimatter, why we only know left-handed neutrinos whose spin runs counter to their direction of motion, or how dark matter is created. But if mirrored or cyclic universes are still not exciting enough for you, you might be satisfied with the idea of a multiverse. This is essentially based on the model of chaotic inflation, and thus of the expansion of the cosmos faster than the speed of light. After the Big Bang put forward in the 1980s by the Russian cosmologist Andrei Lind, this theory proposes that inflation is triggered by a scalar field, that is, a field that takes on a random value. At each point, in some places, the values are just right to set inflation in motion, but not in others. As a result, inflation does not occur everywhere at the same time, but sometimes earlier and sometimes later. But the places where this happens grow exponentially, creating a kind of space bubble, whose inflation slows down at some point and is replaced by normal expansion. However, this network of countless expanding bubbles also constantly creates new bubbles, each of which represents its own universe, and that also applies to our cosmic world. If Lind's theory is really consistent with reality, what we commonly interpret as literally, everything would be nothing more than one of many bubbles in infinity. But what our neighboring universes might be like in detail is a completely different matter. It's possible that they are also teeming with structures familiar to us, such as stars and galaxies. But perhaps they are also home to worlds where completely different laws apply and where there is no matter at all, because if an infinite number of different universes really do exist, then they also contain an infinite number of variations of laws and conditions. Accordingly, each world has its own individual parameters and settings, and in our world the settings are conveniently tuned in such a way that they produce beings who can puzzle over the greatest secrets of the cosmos. You no longer have to worry about how you will never miss a video from us again. Just press the thumbs up and subscribe now to stay up to date from now on. We'll see you soon.